First of all, thanks everyone for coming to this event. Thanks to the organizers, Olaf, Julia, Stefan, Jonathan, and everyone else involved in this event. It's been a great time. And to start off this morning, I'll be talking about a project I've been building over the last year plus now called Constellation, which is a Chisel generator for network-on-chip interconnects. Oh, I didn't plug in my actual presenter stick. There we go. All right. So starting out, why do we build Constellation? What are we trying to do with it? Well, Slice Lab at Berkeley, we do research in computer architecture, and we're looking at the kinds of chips that people are building these days. And the trend we're seeing is the increasing amount of heterogeneity across kind of all aspects of SoC architecture on these chips, right? So here you see, die shot of the Apple M1, and on the bottom right, you can see a trend, the increasing trend of the number of unique specialized accelerators or IP blocks that are going into various generations of Apple's mobile SoCs. And so this heterogeneity across SoC architecture extends across all the areas of the SoC, right? So of course, the processing elements are getting more and more heterogeneous, more and more specialized. In addition to the standard big little CPU architecture, people are putting unified CPU and GPU on a single die, adding more and more accelerators for machine learning, sparse workloads, DSPs, image processing, whatever, right? So the number of specialized IP blocks is growing. At the same time, memory architectures are also getting more heterogeneous, right? We're not just dealing with a global, unified, cacheable address space. We have cacheable, uncacheable domains, scratch pads, I/O streams from devices, dealing with different coherent or incoherent domains. And of course, the combination of this means that the number of the types of access patterns that these devices are injecting into the memory system are getting more diverse, more application or accelerator specific. And all of these factors means that we have many new challenges, interesting effects to study in SoC architecture and NoC design. So how do people manage on-chip communication on these large SoCs? So this is just of an example, an imaginary topology for the NoC I made up for an Apple M1 SoC. But essentially, shared bus or crossbar architectures don't really scale when you're building chips of this magnitude, right? So building a network on chip has been the standard solution for on-chip communication for decades, right? You want to basically multiplex your routing resources, your wires and your routers across many different communication paths on the chip. And of course, the heterogeneous architecture of modern SoCs with GPUs, accelerators, different types of CPUs present many new challenges to NoC design. So you heard the talk yesterday from Abe about how we've been building Chipyard. It's kind of this test bed for SoC architecture, design space exploration, and research. 2 years ago, a big limitation of Chipyard was that we didn't have a good NoC implementation for Chipyard, right? Chipyard could only build SoCs where the on-chip interconnect was provided by your big standard Tower-Link crossbars. We spent some time looking at existing NoC implementations, what's available in the open source to see if we can implement anything or integrate anything into Chipyard. And there were some limitations here. So of course, there's plenty of open source NoC simulators, and these are well studied in the academic space. But these end up being open source C++ models of NoC behavior. They're generally pretty configurable, but of course, you can't actually implement this on a real chip, on an FPGA, actually do the power area performance evaluations we want to do with Chipyard. On the other hand, there is a wide set of open source NoC implementations. I'll just shout out to a few here: the OpenCelerity NoC, OpenPython NoC, ESP, NVIDIA's MatchLib. These all provide pretty decent synthesizable NoC implementations that have been taped out many times. But the problem with integrating these in a platform that they weren't designed for is that these NoC implementations ended up being pretty highly optimized and targeted for whatever platform they were originally intended for. So we found that it would have been quite a heavy lift to try to integrate one of these into Chipyard. And there are existing open source NoC generators as well, so more flexible generators like the one I'm about to present. Some examples are the OpenSoC Fabric from LBL and Connect from CMU. These are pretty good. They support a pretty large set of NoC topologies. You can mess around with different topologies, different routing algorithms. You can put them on FPGA. But I think the critical missing feature that we found across a bunch of these projects was that they were kind of targeted for doing fast FPGA accelerated performance evaluation of a network on chip. They weren't really designed to actually integrate it into an SoC and have it carry your cache coherent traffic in a deadlock-free, reliable manner. Critically, is missing support for coherence protocols in a lot of these projects. So that kind of motivated the design and the development of Constellation. And I think at the beginning, we came up with like some rough set of goals that we wanted the project to achieve. So first is we want Constellation to be conventional and correct. We're not going to really aggressively optimize the microarchitecture. We want to focus on kind of understandable, correct behavior of the network rather than performance. The second point is we like building Chisel generators at Berkeley, and we're going to build Constellation as a generator. And I think like this point is a little subtle, but I think it is important here. It's not a library of different NoC components that you can put together. It's really designed to be something where you can feed it a bunch of different configs, and it will try to generate what you want and generate it correctly, right? We don't want to have the user like implement a lot of new RTL, new routing algorithms, new microarchitecture when they're trying to use this project. It should be transport focused, so we use TileLink at Berkeley for capture current traffic, but Constellation should be protocol agnostic. So later down the line, we can mess with different protocols, or someone else can extend it with their own protocol if they want. Should be accessible, so whether you're a NoC researcher or if you're an SoC architect, whatever you want, the level of abstraction in Constellation should be appropriate for you. Configurable, of course, as a generator. And finally, chip-centric, right? We want to actually end up like taping out this system and building it in our real SoCs and using it in the chips we build going forwards. So, after like a semester or two, we built Constellation. This is a parameterized Chisel generator for SoC interconnects. We try to achieve most of the goals we set out earlier. It's a protocol-agnostic transport layer. Out of the box, it provides support for AXI4 and TileLink. But you can extend it with your own custom protocols that run on top of the base NoC. It is highly parameterized, so you can build like highly irregular, complex NoC topologies like the one you see on the right. It's kind of like an imaginary chip, but you can see here that this is not really like a regular 2D mesh or ring architecture on the network on chip. The thing is verified deadlock freedom. I'll describe how the generator works and how it can provide us some guarantees about the correctness of the network on chip implementation. And it implements like a fairly conventional NoC architecture, right? Wormhole routing with virtual channel flow control. And this thing just gets drop-in. It supports drop-in integration into any existing rocket chip or chipyard design. And I'll talk about that later as well. So before I get into the details of Constellation, I'll go over like a bit of basics on NoC microarchitecture, just so the terminology is consistent. So in a network on chip, routers are essentially nodes in the network topology graph. This gray box here is a single router. The channels coming in and out of the routers are edges. They go to other routers in the network naturally. When a packet enters a router, it comes in through an incoming channel, and it takes some buffer slot or virtual channel in an input unit. Then it queries a bunch of these resources in the router. The route computer figures out where it should hop to next in point-to-point routing. And then we have allocators for the virtual channels and the big crossbar switch in the middle. Once a packet allocates a virtual channel and a crossbar switch, it can proceed through the rest of the router and make its way on in the next hop. So this is just a simple animation demonstrating the basics of how, like in this case, a 3-flit packet might traverse this network. So flit 0 gets injected into router 0. Inside router 0, it's going to query the route computer, allocate the next virtual channel on the outgoing on the next NoC or on the next router for the next hop. So figure out which one it wants to go to, and then once it's made the decision, it's going to transition to get sent over to the next router, and the rest of the flits behind the head flit in this packet are going to follow behind it. In wormhole routing, right? So eventually it gets to its destination, and you can see these flits are following behind in the same set of buffer slots, and eventually your packet exits the network at the point you want, right? So I think the key observation here for Constellation is that this policy describing how packets traverse a network, this is just a resource allocation policy, right? Like given what resources you're holding, try to figure out what resource you should acquire next, and that's going to describe how the packet flows through the network. Some more about how this guided the rest of Constellation's development. It turns out writing like deadlock-free routing algorithms is really complicated, and it gets even more complicated when you add in like more practical concerns like adaptive routing or support for deadlock freedom, even in the case of having protocols that back pressure the NoC. But if we model this routing policy is just resource allocation. We can describe the problem as just basically like, given where a packet is and where it's going, write some function that determines what resource in the network or what buffer entry in the network the packet should allocate next. And this kind of guided the rest of Constellation's design to a significant degree. It means that Constellation doesn't actually implement the routing tables that describe how packets travel through the network. It actually compiles them from like a higher level description of the routing. And then once it has that high level description, it builds an internal model of the entire set of resources in the network. And it can model how packets will allocate and deallocate resources as they traverse the network. And it can use this model to basically verify that the NoC, or the requested routing algorithm, will be deadlock-free and correct before any RTL is even generated. Right? Yeah, so we can verify correctness properties before RTL elaboration. So this diagram depicts the flow of Constellation. I'll walk through some of this. You start with the user-specified NoC parameters. Then the Constellation runs parameter validation, RTL generation, and eventually I'll show how this goes to, this enables a full system evaluation of a network on chip. So the specifications for Constellation, what does the user need to provide to the tool to generate a NoC? We split up the specification into 3 orthogonal areas. The logical specification is kind of ignoring the actual physical implementation of the NoC, just describe what kind of messages the NoC is expected to handle, right? And what deadlock-free conditions does the NoC need to satisfy. The physical specification is where you actually specify the physical topology of the network, the microarchitectural parameters, how many buffer entries are in each router node, how wide are the channels, and more constraints like this. And the routing specification kind of marries the two. It describes how your logically defined flows will be allocating the resources described by your physical specification as your packets traverse the network. So this is kind of more, practically what the NoC params Chisel class looks like. You can see it actually, I tried to make it match the thing I just described, where these parameters describe the physical specifications, so topology, router microarchitectural parameters. These parameters describe the set of flows that your network is expected to handle. And then this routing relation, which I'll show later, is basically going to be, you'd write a function that ends up describing how your flows traverse your network. So for physical specification, Constellation supports any directed graph. You basically just write a function that describes the connectivity of arbitrary nodes in your network. And then you can see that you can build almost an arbitrary topology using this mechanism. Interestingly, Constellation supports compositional construction of topologies as well. I think this was just kind of useful when you try to build SoCs using this thing. Right, so we can do this thing where we take all the ingress and egress points into a router and lift them onto a separate set of terminal routers. This is so you can reduce the switch radix in the actual critical routing paths. We can also support hierarchical topologies. So for example, we can say that this base topology is a 1D torus and is connecting these two subtopologies, which are just one-dimensional meshes basically. And of course, this is all compositional as well. So you can very quickly build something that looks like this using just 2 lines of configuration code. OK, so I'll skip some of these slides for time. We can support varying the channel width between routers in the network. OK, so for flow specification, this is kind of the logical specification of what kind of packets or flows your network is expected to handle. And so this is actually decoupled from the topology, right? So in these 2 networks, we can say that OK, our set of flows is ingress 0 to egress 1, ingress 1 to egress 2, or all to all. And then that means we can kind of change the underlying topology under the hood without actually having to specify what set of flows are actually possible, right? So this means it's very easy to try a bunch of different topologies for the same set of flows if you're doing some kind of design space exploration. And the other reason why we want to do this flow specification step is that we don't want to under constrain the network basically. Usually, not all possible flows in the network on chip are actually possible, right? You wouldn't have a master sending a message to another master in a typical bus architecture. So this is to facilitate those kinds of optimizations. I think the routing specification is probably the most interesting component of this. You specify a Scala routing function for Constellation. So this is not even Chisel, right? You write this kind of high-level abstract function where the parameters of this function are the unique identifiers of the currently occupied virtual channel and the unique identifier of a potential next virtual channel that the packet might go into. And of course, some properties of the packet. So this function basically says, given a packet that is part of this flow that's currently occupying the source virtual channel, return a Boolean, true or false, whether or not it can progress to the next virtual channel. Right, an example of if this is useful is if we just consider this like relatively simple example, we have a 2D mesh with these like terminal collection routers, and we want to do deadlock-free adaptive routing on this 2D mesh with a 2-channel protocol. This actually sounds very simple, but if you try to implement this just by writing the RTL for the routers and by hand, you quickly run into like lots of little like edge cases that will bite you, right? So, for example, in our protocol, our agents can block the request channel, but the response channel must always make forwards progress. This is kind of to ensure that the entire system can make forwards progress, regardless of an agent stalls or something, right? In order to do deadlock-free adaptive routing, we need to have this thing called like escape virtual channels that use dimension-ordered routing, while the non-escape virtual channels can choose arbitrary minimal routes. And yeah, you can imagine that like writing this entire thing out for every single router node here is going to be a huge pain. And you can definitely get it right. But then, when you need to build another NoC or tweak some parameter, you're going to have to do it again and hope you don't run into any new bugs. So in Constellation, we can do this thing with compositional routing, where we allow these, we provide these sub-routing functions, which essentially implement a subset of the routing behavior. So for example, this blocking virtual subnet routing function divides the virtual channels between subnets, where each subnet is a different protocol channel. Terminal plane routing and escape channel routing kind of describe, more detailed, like other parts of this routing algorithm, like how to jump in and out of terminal routers, how to deal with escape virtual channels. And then at the bottommost level, we have kind of like our base routing algorithms, which are pretty easy to implement if you ignore all the other factors, right? So for dimension-ordered routing, route in X, then route in Y. And for minimal routing, it's, choose whatever gives you the minimal route. So because we can we've broken down routing into these like basic building blocks, we can do hierarchical routing too. So in this case, for the hierarchical topology I showed earlier, in a similar way, we can describe how do we route on the base topology and how do we route on the subtopologies. And Constellation will basically stitch all of this together into like a consistent global routing policy. Parameter validation. So once we have a routing algorithm, once we have all the parameters, Constellation constructs an abstract channel dependency graph of all the virtual channels in the network, and then performs graph analysis on the thing to just verify properties like deadlock freedom. Can your packets reach their destinations? Can they do so without encountering circular dependencies, which would cause deadlock? Can protocols back pressure ingresses or egresses into the network? And can the network still make forwards progress under those conditions? So once Constellation verifies these properties, there's some degree of confidence that the resulting network will be correct and it won't deadlock or lock up. OK, so the actual RTL generators for the routers themselves aren't really that interesting. It's pretty much a pretty conventional router microarchitecture. The default is 4-cycle hops, but we can configure it down to 2-cycle hops if we want. So yeah, it ingests the validated parameters and has some configuration settings. Right, so to generate the routing table in each router, we basically compute all possible paths for all possible flows through the network. And for each router, we compute, at the Scala level, precisely which packets might arrive there. And then so now we can construct this abstract truth table, right? Just construct this truth table that maps the, the packet or the flow identifier to a set of, a mask essentially describing the output virtual channels that the packet can allocate next. And then this gets fed into the Chisel QMC algorithm to generate a minimal hardware implementation of the routing table. Right, so like I said, the microarchitecture isn't too interesting here, but there are some configuration options. We can change the pipelining, reduce credit stalls, credit delays, and also switch around a couple of different options for allocators, like the standard virtual channel allocator algorithms. OK, so you have this NoC, you have this bag of routers. How do you actually drive packets in and out of it? The endpoint interface in Constellation is deliberately very simple. You specify whether your flit is a head or tail flit. You specify your payload, and then the identifier of where this packet is trying to go to. So this egress identifier is actually independent of the physical topology of the network. It's just some abstract ID that gets assigned to the ingresses and egresses. So at this stage, for this very basic, almost internal-only protocol, we can generate a very simple evaluation harness in C++. So there's a C++ and DPI interface to the NoC, as well as an abstract class for specifying a traffic model. So we can plug in some C++ code here that will inject traffic into the network. And this entire framework can measure per flow, median, and max latency, throughput, all the metrics you want when you're doing a NoC performance evaluation. And we have examples in Constellation how you can specify a rate-driven traffic model or net trace is like a standard format for like network on chip traces, and we could like load these trace files and inject them into the network as well. Right, and these traces have been collected. I think this work was done like a pretty long time ago, but they collected a bunch of traces from like real parsec multi-core benchmarks. OK, so for actually integrating the NoC into an SoC, you need to connect it to a protocol. And that's where we have these things called protocol adapters, which basically convert from like a standard high-level protocol like TileLink or AXI4 or whatever, down to like the abstract internal protocol in Constellation. So it's pretty easy to extend this with your own protocol adapter, but out-of-the-box support is provided for TileLink and AXI4. And finally, this is all integrated into diplomacy. So if you're not familiar with what diplomacy is is kind of like this rocket ship component that lets you stitch together a bunch of different devices into like a bus architecture very easily, and add in like widgets that represent things like buffers, arbiters, crossbars, or now a NoC in that memory system graph. So this is a drop-in replacement for existing TileLink crossbars and AXI4 crossbar generators in rocket ship and Chipyard-based designs. So right where previously you just have this fully connected crossbar, you change one configuration option and you can drop in a Constellation network on chip here. And so we can test both at the standalone like bare protocol level, and also connect this up to like TileLink traffic generators, fake TileLink memories, and just verify that everything can make forwards progress. All this testing is done in continuous integration. It's set up on GitHub. It's great for open source projects. Highly recommend it. Even for my own sake, it was really nice just to, whenever I pushed the PR to this thing, it generated like 100 different NoC configurations and basically torture tested each configuration to make sure that nothing would hang or lock up or throw an assertion or something. So this was a very nice to have. GitHub Actions is great. OK, yeah. So for SoC integration, you can see the standard Chipyard block diagram. Any of the blocks is highlighted here, which are normally just TileLink crossbars. We can drop in a Constellation NoC. So a little bit more practically, what does this look like? Say I want to build, this is like my example floor plan, right? And I want a 2D mesh interconnect for all the core to L2 traffic. But for L2 to DRAM, I want like a unidirectional torus for some reason, right? So this is kind of what the Chipyard configuration class looks like for this network on chip. So down here, you kind of see we're specifying like the number of cores, cache banks, DRAM channels. And all of this block is kind of configuring the network, right? So here, for each of the buses we're replacing, whether it's the control bus, memory bus, or system bus, we specify the configuration of the NoC, so like the topology, routing algorithm, channel parameters. And then we specify in this dictionary basically a mapping between cores or agents to physical nodes on the network on chip. Right, and so this, you basically have to craft this somewhat carefully, but if you make a mistake, the generator will tell you about it. And then this makes it pretty easy to generate like this NoC topology, where in this case we have independent networks for the system bus and the memory bus on the system. But what if we want to do something different, where we want to have a single interconnect for all the traffic on the chip? That is possible as well, because we can layer multiple logical interconnects onto a shared global Constellation network on chip. So in this case, instead of providing a configuration per bus we're replacing, we provide this like global NoC parameters, which describes the topology for like a giant shared NoC for the system. And then in a similar fashion for each of the buses, the system bus and the memory bus, in this case, we specify a dictionary that just maps them onto positions in that network on chip. In the previous example, that basically built this design where you had like a hierarchical topology with like a base 1D unidirectional torus, and then two subtopologies that are 1D meshes. So we can also, something which I want to do in the future is develop new protocols that can run on top of Constellation, right? Not everything has to be, cache coherent TileLink or even AXI. Depending on what we're trying to do, the kind of messages we're trying to send throughout our system, we can develop, our own custom protocol and map that relatively easily onto a single shared Constellation generated network on chip. From scaling out, we can build these like relatively large systems here. In this case, we have 72 coherent RISC-V cores, 32 slices of LLC, 4 DRAM channels, and there's 78 nodes of router in this NoC. So last year at Micro, to show this is really easy, we ran a tutorial at the Chipyard Firestorm tutorial, and part of that was basically having the attendees configure a Constellation network on chip on their own. Generate the network and evaluate some very simple workload running on top of it. Just for fun, this is kind of what they did in the tutorial. They configured some agents on a network. They ran a simulation in Verilator, and we were able to configure it to get it to generate like this animation of all the network traffic as the thing's running this like somewhat trivial benchmark, like a multi-threaded memcopy. But you can see see the network traffic as the various nodes are accessing the cache banks, and the cache banks are accessing memory. Constellation has been taped out. This was a class chip, the one I talked about yesterday. I actually handed Constellation to the undergrads as a generator that they can use. I feel like if your project is robust enough for a bunch of undergrads in tape-out course, then it's a pretty, it provides some confidence to me that it seems to be OK. So they configure the generator, perform physical design on the thing, and you can see the red highlighted here is the various router nodes in the resulting network. So yeah, maybe it's OK. I don't really know. I wouldn't bet my life on it, but seems OK for now. I'm a big fan of Chisel. Jack's in the audience. I want to talk about like the experience of building Constellation. So this pie chart shows like how many lines of code were in the various parts of Constellation. You can see that in the actual RTL for the router itself, it's actually very, very compact. Much of the work is actually in implementing these adapters just to deal with like diplomacy and then the protocols. And then like a lot of the testing code, right? The things that are actually injecting traffic into the network just to test it. That actually took a lot more of the code. But I think the takeaway from this is that like compared to something like an accelerator or a core, a NoC is like a relatively easy, simpler microarchitecture to implement. Integrating with diplomacy was pretty complicated. It's probably the like least easy part of this, but it was very worthwhile just to make everything work with our systems. I think this is actually a really good use case for Chisel because the architecture of a NoC is like you have a lot of these like very similar but not quite identical elements in the system, right? Like every router node is like has roughly the same microarchitecture, but they have a bunch of like parameters dictated by where they are in your global topology. And so having this like reusable router RTL generator that just gets stamped out a bunch of times is a good pattern, and it matches like the Chisel generator approach. And finally, I think this is something which I don't know. It's the approach to Constellation was basically we want to write less Chisel and try to do everything at the Scala level as much as possible before going down to the Chisel generator, which is actually going to build our RTL for us. Unfortunately, there is some generalization cost here. Constellation isn't the fastest NoC. It's not the most efficient NoC. But the benefits is that it's fairly understandable and it implements a fairly conventional design. Yeah, this is my last slide. Constellation is a parameterized Chisel generator for SoC interconnects. It's been open source. It's integrated into all the Chipyard releases now. There's documentation. There's plenty of examples, both of like the whole SoC architecture integration, but also kind of like standalone. When you just want to evaluate the NoC by itself, there's examples on how to do that as well. There's a link to the repo, and you can find the documentation next to the repo as well. All right, so thanks everyone. I'm happy to take any questions if there are any.
Thank you. Questions?
Hey, great talk. If I wanted to add my own NoC component to Constellation, like what would that process look like?
It depends what your component is, like a router or like an allocator.
Say like a wormhole concentrator or something.
Yeah, that is kind of tricky right now. So the way I see it is that the router RTL generator is kind of like the implementation right now is like the baseline implementation. It implements like the very standard wormhole routing system. If you wanted to implement your own like more custom router that implements like a different flow control or whatever, you basically need to replace this entire orange block with your own stuff. So I think there is some reason why that's not totally like a bad idea, because you can still reuse a lot of the code, which is like testing whether your topology makes sense, whether your routing is deadlock free. But the actual RTL generator component, as long as it has the same parameters, it should still be OK. But you have to kind of like replace everything in that level. Yeah.
Jerry, this is really interesting. I'm wondering about the part where you're saying about the interface into the network and having these kind of these IDs that are perhaps kind of arbitrarily assigned during the allocation. And I wanted to understand, how does that map over when you then connect with the coherence protocol, and you have things like share vectors that need to track, the exact IDs that people have.
Right. So I guess that's like, that happens in different layers, right? So the part which Constellation needs to deal with, I guess, if I can find this slide. Yeah, so these protocol adapters, where they create these IDs, these IDs are actually, they aren't really related to any IDs that the protocol knows about. So like the protocol will assign its own like source IDs or sync IDs, but that just gets shifted in with the payload into the packets, right? So these IDs for the ingress and egress are just based on like decoding the address that, typically if you're using address-based routing, it's, you just look at the address and figure out which agent it's going to. You would want to, the protocol adapters basically construct that like map between addresses to destination points in the NoC.
Okay, so basically you might just like end up with an extra flit somewhere in your control.
Yeah, so yeah, there is like some, the most naive thing to do is to just take your entire protocol message and just like pack it in this payload. But oftentimes there's stuff which you can like deduce at the endpoint from like the other field. Like if you know the ingress field, then you can like reconstruct the source ID in some cases, right? But that's kind of like an optimization which you would implement on top of the space system.
Okay, understood. Thanks a lot.
Cool. Jerry, I have a quick question. So I know very little about NoCs. I've been able to get away so far without ever using one. How does this compare with sort of the state of the art, that you would buy from a, top tier proprietary vendor?
So there's a lot of features which Constellation can't do, right? I think like overall the high-level architecture is pretty similar. The latency through the network is much slower than what you would find in a modern high-performance system, right? 4 cycles as default is very slow. You can get away with like 1 cycle or 2 cycle hops in most modern implementations. Critically, it's missing features for like being able to turn off parts of the NoC while keeping the others online. That's pretty necessary when you're building these scale-out systems. We don't support that yet. And the other one is QoS, right? Being able to specify, provide guarantees on how much traffic is able to make, like how much bandwidth the NoC is able to provide to certain flows. We can't really provide any guarantees on that besides, what we can measure from seeing the thing simulate. Yeah.
Cool.
Hi.
Yep.
This is really interesting. Could you talk a little bit more about how you specify agent behavior at the protocol level? Is that through the flows or? Yeah, so for now, the main protocol constraint we have to deal with is, okay, so I guess at the protocol level, there's 2 things, which is, let me try to find that slide. Right, it's these flows describe like which agents can talk to each other, right? So at the protocol level, you would break down a protocol into multiple channels, and each channel gets like a unique identifier for possible flows. So like from master 0 to slave 0, the request path is like one flow, and the response path the other way is another flow. And those all get like unique identifiers that you kind of generate when you're mapping the protocol down to the network, like based on like what the channels are and what's allowed. The other part of how protocol specification comes into this is dealing with like blocking behavior between protocol channels. So like the example I mentioned where an agent can block requests, but it needs the responses to make forward progress. You specify that at this level too, and this adds like constraints on the like the deadlock checking to make sure that everything still works. Right.
Hi, nice work. I have a question about the clock. Do you assume that you have a source synchronous clock all over, or do you have something else?
That's one of the limitations right now. We assume there is like a global synchronous clock across the entire NoC. I've tried to implement like clock crossings between routers, but I did not end up finishing that. That's probably something we need to do. But yeah, currently it implements like it assumes like a global synchronous clock.
Yeah. Hello. Yeah. Great work. So you mentioned that you taped this out in the Tapeout class. I was wondering, was that directly because you were maybe trying to test out this design by taping it out, or because in the class you were distinctly trying to fulfill the need of creating a NoC?
It wasn't necessary for the class chip, if that's what you're asking. But it was, we wanted the students to build something a little bit more interesting. And, out of my own self-interest, I wanted them to, use my stuff. So I could, as a TA, I could basically mandate that.
Yeah. Are there other research projects that you are taking advantage of the Tapeout class to tape out new designs?
Yeah, I think we've tried before. Like, we tried to put Boom in the Tapeout course. That ends up being a little bit more difficult. Like, I was pretty concerned initially that Constellation, the physical design, would be very difficult and they wouldn't be able to push it through. But it seemed to be okay for the class at least. But yeah, like generally, sometimes we'll try to put research stuff on the Tapeout class, but it depends on the situation and whether there's someone willing to push it through, basically. Yeah.
Thank you.
Daniel, thank you, speaker again.
Thanks, Jerry.